Hi, everybody. Thank you for joining me for this next lecture. This is lecture 4, and today we're going to be discussing the mean, median, and mode, range, variance, and standard deviation. So we're going to start with the mean, median, and mode, which are classified as measures of central tendency. We can use the mean, median, and mode in countless scenarios, but in this lecture, I am going to focus more on allied health. So in medical and allied health fields, data is essential for making informed decisions regarding patient care, resource allocation, and clinical interventions. Understanding measures of central tendency, which are the mean, the median, and mode, allows healthcare professionals to summarize and interpret data effectively. These measures help to describe the general pattern of data, providing insights into the center of a data set. So measures of central tendency help us define what is one typical or common or normal for a group. So we'll start with the mean, which is commonly known as the average. And it's the average of a set of numbers. It's calculated by adding all the values in the data set and dividing by the total number of values. So if you're dealing with a sample, the sample mean is the sum of all the sample values divided by the size of the sample. The symbol that we use to denote a sample mean is X with a bar over it. We call it X bar. It's the mean of a sample. And mathematically, the formula is take the sum, that is what this big Greek sigma symbol stands for, take the sum of all the data values x and divide by the size of your sample. Doing that, you will get your sample mean x bar. Okay. Sigma x is the sum of all the values in the sample, and lowercase n is the number of values in the sample size. Okay, sometimes when you're dealing with a population, you'll need to find the mean of the population, and we will also be able to do this using the same formula, but the symbol we use to represent the population mean is different. Instead of X bar, we use the Greek letter mu, which looks like a U, but with a longer tail in the front. It is still the sum of all the data values divided by the total, but in this case, the total is the size of the population, capital N. Okay, so that's the mean, something that most students have heard of before, add up all the values and divide by the total. But in this class, you are going to make sure that you understand the difference between a sample mean and a population mean. And the difference is basically in the symbol that we use. The formula is generally the same. So let's find the mean of a set of cholesterol levels. If we have values 180, 195, 205, 220, and 240, so we have 5 patients, and these are their cholesterol levels, we can find the mean by adding them up and dividing by 5. So I'm going to share my calculator, and I'm going to do that with you. So here we are on the home screen of the calculator, and I'll just add up 180 and 195, 205, 220, and 240. And then divide this answer. So I'm pressing the divide sign and 5. The average, the mean cholesterol level is 208 in this case. So since these numbers, these 5 numbers that we found the sample mean for, since they are part of a sample and they're not a population, because we're told here that it is a sample, We are going to use the symbol X bar to represent the answer, 208. So the math is still the same, whether or not it's a sample or a population. We still add them up and divide by the total, but the symbol we use is different for a sample. Okay, if we were looking at cholesterol levels for an entire patient population, we would use mu instead of X bar. Let's look at some other applications. We could be finding the mean blood pressure. The mean value of blood pressure readings in a sample of patients can help estimate the population mean. For instance, if a sample mean of blood pressures can be used to infer whether a population has hypertension. We can also calculate the mean length of stay in a hospital. Calculating the sample mean of hospital stay durations can help hospitals make projections about the population's hospital stay trends. We could also calculate mean blood glucose levels to monitor diabetic patients over time and help doctors adjust insulin dosages. So we do have some mathematical limitations of the mean. And one of the limitations is that it's very sensitive to outliers. And if you remember our discussion on outliers when we talked about the stem and leaf plot, outliers are those extreme values at the far end of a distribution. We saw examples where the outliers were on the far high side, the right side of a distribution, but the extreme values can actually occur either on the left or the right. And what that tends to do with an average is either drag the average way down if the outlier is on the left or the low side, or inflate the average if the outlier is on the far right or the high side. So for example, if you have one patient in the data set from before with a cholesterol level of 400, which is extremely atypical, it would increase the mean dramatically, even though it doesn't represent the typical patient's level. So imagine if you were to add 400 in here, it would take and instead of, let's see, what was the other one? The other value, okay, it was 240. So let's replace it with a 400. And that's what we're doing here. Okay. And when you do that, you're going to inflate your average to 240. So this extreme value on the far right inflates the mean. So it's an inflated mean. So it is very sensitive. The mean is very sensitive to these outliers. So let's look at the median. The median is the middle value in a data set when the data values are arranged in ascending or descending order. If there's an even number of values, the median is the average of the two middle numbers. So if you have a data set, for example, this set right here, the first step in finding the median is to change these numbers to be in ascending order from left to right. So I have 1, 2, 5, 7, 9, 9, 9, 11, 13. And once they're in order from left to right, you find the middle one. So since I have 9 numbers here, the middle number is the fifth. Okay, 1, 2, 3, 4. The fifth number is the middle number, and it's 9. So we put them in order, we find the middle number. If there are two middle numbers, middle values, calculate their average. So let me show you that example. Okay, we have 5 patients from a clinic with cholesterol levels. This is the ones that we had done before on the calculator. Put them in order from low to high, and the median is the middle. So putting these numbers in order, the median is the third number because we have 5 values, so the median is 205. So if we add a sixth patient here, and there's no one middle number, we have to take the average of the two middle numbers. So adding a sixth patient, in this case with um, cholesterol level 245, we have two middle numbers now, 205 and 220. So the median is the average of the two of them. So adding 205 plus 220 divided by 2, we have a median of 212.5. The advantage of the median over the mean is that the median is resistant to outliers, where the mean was sensitive to outliers. So here's what happens when you have an outlier in a collection and you find the mean. If you insert a person with a very large cholesterol level of 300, for example, into your data set, the median cholesterol level is going to be mostly unaffected. It may be slightly affected, but it will be mostly unaffected by the extreme value, whereas the mean would be very much affected. So let's take a look. Let's take away that 245 and change it to a 300. So we now have this extreme value in the data set. The median is still the average of the center two. 205 plus 220 divided by 2, the median is unchanged. No matter what this high extreme value is, this is like an extreme outlier, the median is unchanged. So an unchanged median. And if you think about it, this 300 could actually be a 400. And it would still have a median of 212.5. The median would remain unchanged. So some other applications of the median, we can calculate a median survival time. If we're looking at clinical trials for cancer treatments, researchers often report the median survival time, the point at which half the patients are still alive and half have passed away. This measure is not affected because we are trying to stay away from the extreme values here, the outliers, by extremely long or short survival times. So outliers in this set would be ignored. So we wouldn't consider the patients with extremely long survival times or extremely short survival times. The median is the center regardless of those outliers. Another thing that we can measure with median, and it's often done with, in many cases, either it's both in medicine and every other case you can think of with income. When we look at people's income tends to be better measured when looking at a median instead of a mean. The median of an income um, is best looked at when you look at the median, or rather the measure of the center is best when you're looking at the median because you're not affected by those really, really high incomes in a group or really low incomes in a group. Another thing that can be measured with the median is drug efficacy, the median time to symptom relief. Okay, how much time does it take for a symptom to go away or be relieved? Outliers are the patients who respond either very, very slowly or very, very quickly. They would be ignored when you're looking at the median, and you would just be looking at the very center of this distribution. The last measure of central tendency is the mode. The mode is the most frequent value in a data set. So when you're looking at a graph, a mode is the highest point, the most frequent value. There may be no mode if there's no one number that appears most frequently. There may be one mode that we call that unimodal, we may have two modes, that's bimodal, or more than that, we may have something that's multimodal. Often in this class this semester, either we have one or two modes. So imagine that we look at a set of numbers that represent daily doses of medication administered to patients in a hospital. One dose, two dose, and these are for per patient. So one patient had one dose, one, two, three patients had two doses of medication, and two patients had three doses of medication, and one patient has four doses of medication. The mode, the number that appears most frequently there is two. So two would be considered the mode in this case. Here's a patient BMI example. Body mass index, BMI. So if we look at patients' BMI, we can categorize weight status. And suppose we have these clinical records. Suppose we have a BMI categorized under 18.5, and there are three patients in that category. And then we have a BMI between 18.5 and 24.9. We have 10 patients in that category. And then we have BMI between 25 and 29.9. We have 7 patients in that category. And obesity is BMI greater than or equal to 30. We have 4 patients in that category. The normal weight BMI between 18.5 and 29.5 for 10 patients has the highest frequency. So 10 is greater than 3, 7, and 4. So the normal weight category is the modal weight. So the most frequent BMI category is normal weight. 10 patients fall into this category. So it can help the clinic focus resources on prevention and education programs for patients in the most common BMI category, also identifying areas where weight management might be needed. So measures of central tendency, the mean, the median, and the mode talk about the most typical of a value in a distribution. We are not concerned with the outliers on the far left and far right when we talk about mean, median, mode, although we do see that the mean is affected by those outliers. For the most part, our measures of central tendency we are interested in knowing what is typical and what the center of a distribution looks like. So let's look at another example of mode. In a hospital setting, doctors may administer various doses of a medication to treat a particular condition, such as pain management. Suppose the doses given to 20 patients are, and we have 10 milligrams were given to 3 patients, 20 milligrams were given to 8 patients, 30 milligrams given to 5 patients, and 40 milligrams given to 4 patients. The highest frequency, the most patients received 20 milligrams. So we say that the mode dose here is 20 milligrams. It was administered to the most patients. So this information can help doctors understand the typical dosage most patients respond to. That's what a measure of central tendency is trying to analyze. Typical. Ensuring that they have adequate supply for 20 milligram doses on hand while also guiding them in evaluating standard dosing protocols. Okay, so that's the meaning of the mean, median, and mode. Let's take a look at how we would calculate them, the mean and the median on the TI-84. The mode is not something that's calculated through the function that I'm about to show you. So the mode is something we would just simply count to find the highest. So the mean and the median. We're going to put numbers into a calculator list like we've done in the past couple of lectures. And then we're going to run a function called 1var stats. So putting these numbers into a list, and I'm going to put in this set of values right here into my list on the calculator. After I run it, or after I enter these numbers, I'm going to run a function and I'll show you the output. So let me switch to my calculator right now. These are the numbers I'm putting in. If you want, you can pause the video and put these into your calculator now. So with the calculator open, we press Stat, Edit. If you have any data in here from a previous lecture, you can go up to the name of the list, press Clear, and Enter, and that would clear out the list. But I'm going to put these new numbers in: 4, 5, 6, 6, 6, 7, 7, 7, 7, 7, 7, 8, 8, 8, 9, 10. So the numbers are in L1. They happen to be in ascending order, but they don't have to be when you do this calculation. You're going to press Stat, and now, the first time we are doing this, we're leaving the Edit menu and we're going into the Calc menu. So using your arrow to the right, go to the Calc menu, and with number 1 highlighted, press Enter. This is one variable statistics. One variable statistics asks us for the location of our data. So we're going to specify list 1, second, number 1, or wherever your data is. Frequency list can be left blank for now, and calculate. Okay, so leave frequency list blank, press calculate. The very first line of this output gives us x bar equals 7. That is the mean of our values. There are other output lines being output here, and I'll quickly go through them, but we don't use we don't use sigma x or sigma x squared. Okay, sigma x, the sum of all the values. If we were to add them all up, they would give us 112. Sigma x squared, if we were to square all those numbers and add up the sum of those squares, we would get 816. We also do not use that. But we do use the next two, and I'm going to spend a lot of time with these. Sx and sigma x. These two are going to be important in a few moments when we discuss measures of variability. So we're going to come back to these two in a minute. The size of the sample is 16. The minimum value, we're going to be talking about min and Q1 in a minute. Use your arrow down button to get to the next page. Okay, and you see MED come out. MED equals 7. So the two numbers I want to pull out right now are the median and the mean. X bar equals 7 and median equals 7. So with those numbers, let's go back to the slideshow. The median and the mean are both 7. Okay, so we put these into our calculator. We ran the function 1var stats, and okay, we want to take note of the mean and we want to take note of the median. Now the calculator, no matter what our data represents, a sample or a population, the calculator will always use the same symbol here, X bar. So you'd have to know if your data represents a population, the proper symbol to use is actually mu if you're dealing with the mean of a population. If your data represents a sample, you use X bar. The calculator does not distinguish. The calculator will only give you the mean, the symbol for the mean of the sample. There is no symbol for a median, so it's just denoted here by MED. So the mean is the first line, that's x bar equals 7, and the median is noted by MED, and that's also 7. Why do you think the mean and the median are the same here? So the answer lies in the shape of this distribution. This distribution, and this is what it looks like. It goes from 4 and then it increases, and it goes to 7, 4, 5, 6, 7, 8, 9, 10. But look at the frequency of the numbers as we go through this list. We have only one 4, only one 5. We have 3 6s, 6 7s. Then we go back down again, 3 8s, 1 9, and 1 10. So when we graph this, we'll see that it is perfectly symmetrical. So this is what, I'm not going to ask you to do this histogram on your calculator, but if you label the center if you label the horizontal axis with the numbers in the distribution 4 through 10, and the height of the bar is the frequency, you see that we have 1, 4, 1, 5. This is a 3. There are 3 6s and 3 8s, and there are 6 7s. Okay, and there's 1 9 and 1 10. And it's perfectly symmetrical. What you see on the left is exactly what you see on the right, and the center is right in the middle with the number 7. And that's actually a rule with symmetrical distributions. Symmetrical distributions will have the same exact mean, median, and if you see it right here, also the mode, which is size 6, but the value down here is 7. Oops, I messed that up, but it's just the number 7 here. So in a symmetrical distribution, the mean, median, and mode are all the same, in this case 7. Okay, I want to take a look at what it looks like to be in a skew distribution now and how that makes the mean, median, and mode appear. Let's put this set of numbers into L2 on our calculator. Okay, so going back into the list, press Stat, Edit, and now let's move over to 2 and put the numbers 4, 5, 6, 6, 6, 7, 7, 7, 7, 8. And let's calculate the mean and the median for this data set. I can spot that the mode is 7 because I have 7 appearing 4 times, and that's the most of any of these numbers. But the mean and the median, let's run stat, then calc, then number 1, specify L2 here. The mean is 6.3, and the median, let's scroll down, the median is 6.5. Mean is 6.3 and median is 6.5, and we saw from the appearance that 7 by counting is the mode. So let's go back to the slideshow with those numbers and see what this means. Okay, so this is just running through what we just calculated. We have the mean 6.3, the median 6.5, and when we examined the number of values, we saw that the mode was 7. What kind of distribution is this? Well, I'll give you a hint. It is not symmetrical because the mean, median, and mode are not the same. It is a skewed distribution, and in particular, it's got a skew in one direction versus the other. So I'm going to, and let's take a look at these numbers again. 4, 5, 6, 6, 6, 7, 7, 7, 7. I forgot, and then an 8. So what it's going to end up looking like is we're going to see a high part of the graph on the right side, and it's going to trail off on the left. Do you remember what that's called? It is a skewed to the left distribution. This is a skewed left distribution. So if we were to create a graph that has each of the bars represents the number of values we have in that set. So there's 1 4, there's 1 5, and there's 1 8. and then there are 3 6s and 4 7s. This is what this graph would look like, and it would tend to look skewed left. There's a longer tail on the left, and we see that with our skewed distributions. Now, in skewed distributions, unlike symmetric distributions, we don't have the same mean, median, and mode. They are all different. So we still have a mode of 7 because that is the number with the highest frequency, and we noted that when we were counting the values before, but the mean and the median were 6.3, the mean and the median 6.5. And there's the mode right there. So what happens in a skewed distribution is your measure of central tendency that is most affected by the outliers gets pulled down to the left. In a skewed left distribution, the median is most affected by the values on the left-hand side, by the 4 down here. Now, it doesn't necessarily mean that 4 is an outlier, but it just means that the mean is most affected by that value on the far left. The median is somewhat affected, but it's not as affected as the mode. So it's 6.3. It's not, I'm sorry, the mean is 6.3. The median 6.5 is not as low as 6.3. So while it is pulled down away from the mode, it's not pulled down as much as the mean. And the mode is always the point of highest frequency. So these are the positions of the mode, the median, and the mean in a skewed left distribution. And that actually will always be the case. The values may be different, but we are always going to see in a skewed left distribution that the mode is the point of highest frequency. The median is dragged out a little bit lower than the mode, and the mean is dragged out the most away from the mode towards the direction of the skewed tail. And we see that in all skewed left distributions. Let's look at the other direction. Let's look at skewed right now. Putting these numbers into our calculator, we're going to find the mean and the median again. So I'm going to put this into L3. We're going to put 6, 7, 7, 7, 7. Okay, so it looks like 7 is still the mode here. 3/8, 9, and 10. So calculating the mean and the median, stat, calc, number 1, use L3. The mean, 7.7, and scrolling down to find the median, 7.5. So 7.7 for the mean, 7.5 for the median, and 7 for the mode. Okay, so reviewing what we just did on the calculator and taking note of our values, the mean 7.7 and the median 7.5. This distribution, also skewed, is in the other direction. It's skewed on the other side, so this is a skewed right distribution. And if we were to graph it, we have 1, 6, and 4 7s, 3/8, 3/8, and 1 9 and 1 10. It is a skewed to the right distribution. And in a mirror image of what occurs in the skewed left distribution, the mode is the point of highest frequency, and we said that was 7, but our mean is greatly affected by anything in the right tail. So our mean is going to be pulled upward to the right with a 7.7. So let's put right there about the mean. And the median going to be pulled up to not as far as the mean, but it is still going to be pulled up. It is 7.5. And the mode unaffected is the measure of central tendency that is least affected by anything going on the left tail or the right tail, and that's 7. So we will see that relationship in all skewed right distributions. You're going to see that the mode, always the point of highest frequency, the median is going to be pulled out in the direction of the skewed tail, and the mean is going to be pulled out even further in the direction of the skewed tail because it is least resistant to the extreme values on the far right. So the next thing we're going to look at, now that we've seen mean, median, and mode, and we understand the relationship to skewed and symmetric distributions, we're now going to look at the measures of variability. Now, these are different than the mean, median, and mode because we're not only interested in what's going on in the center, we're going to look at the whole distribution. So measures of variability tell us about dispersion, or how a distribution is spread out. In medical and allied health fields, knowing the average or central value of data is important, but it's not enough. And this is true for most fields. Healthcare data can vary widely between patients or situations, and understanding this variability is crucial for making informed decisions. The range, standard deviation, and variance are measures of variability that describe the spread or dispersion in a data set. These measures help healthcare professionals determine how consistent or inconsistent data values are within a group, which can have significant implications for patient care and clinical practice. So, what does variability look like? Well, looking at data set 1 as compared to data set 2, they both have 5 different numbers, but look at the differences in data set 1 and look at the, oh, I'm sorry, there's 2 5s, so it's not 5 different numbers, but 4 different numbers. Look at the difference in values in data set 2. When we are measuring variability, we are specifically interested in how different the numbers are from one another. Data set 1 has little variability. They're relatively close to each other, those values, even though they are mostly different. Dataset 2, on the other hand, has a lot of variability. The data values have a great variation. They go all the way from 1 to 100. A measure of dispersion, or a measure of variability, is a single number that tells us about the variability in a data set. There are 3 measures that we're going to be doing here: range, standard deviation, and variance. We're going to be calculating each of them, and they are going to be telling us about the variability in a data set. So when we calculate a measure of variability on data set 1, the number that we calculate is going to be low in value, meaning that there's a low measure of variability. And when we calculate measures of variability on data set 2, the numbers we calculate will be higher in value, indicating higher variability. The first one that we look at is range, and this is the simplest measure of variability. It's just the difference between the largest and smallest data values in a data set. So if you have your max and you have your min, you just subtract them, and that is your range. So imagine you have patients at a diabetes clinic, and your youngest patient is 22 and your oldest patient is 75. The range is the difference between the oldest and the youngest. So taking 75 minus 22, you get 53 years. That is the range. The range doesn't tell you anything about what's going on in between those values. So you don't know anything about these other numbers in the data set when you look at the range. You only know how big a span your data measures. So some applications of the range: If you know the range of ages in a clinic go from 22 to 75, you can influence decisions, or your data can influence decisions regarding the types of treatments or interventions that are appropriate for different age groups. So knowing that you do have young people in this data set, as well as older people, you can change your process. Measuring the range of heart rates in patients during a stress test can help determine the spread of responses to physical exertion, indicating whether some patients may need further cardiac evaluation. The range is very sensitive to outliers. Extreme high or low values can distort the result. So, for example, one elderly patient in a group with a much higher age can make the range seem large, even if most patients are in a narrow age group. So the range doesn't tell us everything, it just tells us about the two endpoints of a data set. So that's why we do need more. We need more for measuring variability. The variance is a little bit better than the range because it gives us a measure of dispersion that considers all the data values in a data set. So we're not just looking at the endpoints, we are looking at everything in between. It gives us an idea of how much the data values spread out or deviate from the average. A higher variance indicates greater variability in data. We use two different symbols for the variance. We have this lowercase Greek sigma squared. That is the variance of a population. We also have the variance of a sample, and it is S squared when our data represents a sample. And we have these two formulas that we use in statistics. We are going to be applying this through our calculators, so we're not going to be using these formulas by hand or working with them by hand. We are going to use our TI-84s to calculate these for us. So the variance gives us a measure of dispersion. A higher variance means that you have more variability. Higher variance means greater variability, and a lower variance means lower variability. So in that beginning slide that I had with the numbers 4 through 10, and then another next to it, I had a data set 1 through 100. There would be a higher variance in the data set 1 through 100 because there's more variability there. So let's look at an example. So imagine we're studying blood pressure of patients, and most patients have a similar BPI around 120 mmHg. So if most of the patients are consistently measured blood pressure or have consistently measured blood pressures around 120, then we'll have a low variability. Our variance will be low. For example, I'm going to show you on our calculator that if we were to calculate the variance for these 5 numbers, we would get a variance of 2.5, and it's in square units. Okay, it's one thing to remember about the variance, that it is in square units. On the other hand, if the blood pressures are spread out, and some patients have very high blood pressures and some patients have very low blood pressures, we're going to have a higher variance. So this indicates a greater difference between all of the patients' blood pressures. So imagine blood pressures that range from 100, then they say 110, 120, 140, 160. That's more variable than this set right here with the 118 through 122. So measuring the variance on this second set of numbers is going to give a much larger value, and in this case 580 mmHg squared. And I'll show you how to do that on the calculator as well. Much higher variance is associated with greater variability in our sets of values. The variance is always in square units. So it's in squared mmHg for blood pressure, which can make interpretation more difficult in real world contexts like interpreting blood pressures. So, um, and this is same if we were looking at a variation of people's heights, um, people's heights would be measured in inches, for example, and our variance would be in squared inches. If we were measuring miles, like distance to particular locations, and we found the variance for a set of miles, then our variance would be in squared miles, which sometimes makes things a little harder because you're trying to interpret something that is squared. So there's an easy fix for that. We just take the square root of the variance and we use the last measure of variability. This is the one that's most common, and it is the standard deviation. It takes the square root of the variance, and therefore the units go back to being the same. So if they were mmHg to begin with, then the squaring done in the variance is reversed and it ends up back with the same mmHg. If it was inches to begin with, then the standard deviation will be in the same units, inches. So let's look at the standard deviation. It's the square root of the variance. Like the variance, it reflects how spread out the values are, but it's easier to interpret because it's in the same units as the data itself. So instead of sigma squared for the population variance, we use sigma for the standard deviation of the population. Instead of s squared for the sample variance, we use s for the standard deviation of the sample. And these are the formulas. Essentially, it's the same formula as before, but it's just got this big square root in front of it. So we're undoing the squaring process that gives us those square units in the variance to take us back to the original units. I'm going to show you how to do this on the TI-84 now. So we're going to put numbers into our calculator. Let's put this set of blood pressures in that we were talking about before. So we're going to press Stat, Edit. Okay, I'm done with L1, L2, L3. I'm done with those examples, so I'm going to clear out those numbers now. Clear on L1, clear on L2, and clear on L3. Let's enter 118, 119, 120, 121, and 122. Okay, we're going to press Stat and go over to Calc and run number 1. We had done this for the mean and the median, and now we're going to be doing it for the standard deviation as well. Okay, you're going to press the list where your data values are in. I'm in L1. You're going to leave frequency list blank as before, and you're going to hit calculate. Okay. The two rows that we're going to make use of now are SX and sigma X. For the sample standard deviation, we'll refer to the row SX, and for the population standard deviation, we're going to refer to the row sigma X. Now, those 5 numbers that we put into our calculator were 5 sample values. So those data values represent a sample. Therefore, we're going to use SX as our standard deviation, 1.5811. We're going to round to 4 decimal places. So we're taking it out to 4 decimal places. If this 3 after the 1 were 5 or more, we would turn this 1 into a 2. 1.5812 in that case. We're going to keep it at 1 because this is 4 or less. Now, if our data, instead of representing a sample, if it represented a population, we would be using the next row, sigma x, for our population standard deviation, and it would be 1.4142. So let's go back to the slide. Okay, so we have different values for the sample standard deviation, like the calculator shows. We have Sx and we have sigma x, and we choose the one that our data represents. If our data represents a sample, we'll use Sx, and if it represents a population, we use sigma x. So because our data represents a sample, we use Sx, rounding to 4 decimal places. The calculator does not give us a variance. So in order to create, or if you were asked to find the variance, which is not too common, but if you were asked to find the variance, you would have to square the standard deviation. So you would take your 1.5811 and square it. And I did forget to show you that on the calculator, so I'll show you right now. There is a squaring key on the calculator that you can use, and that would take you from the standard deviation back to the variance. Not too common to do that, but you can do it if you need. So I'm going to go to my home screen by quitting this screen. I'm going to remember my sample standard deviation, 1.5811. And there's this key right here. It is to the left of the comma, x squared. If you put that in after your standard deviation and hit enter, it will square it for you. And we are also going to round this number. If we had to find the variance, this is it, 2.499, and we're going to round this 8 up to a 9, 2.4999. Okay, let's take a look at 2 different graphs with 2 different standard deviations. These are histograms, and the histogram on the left, you see that the bars and the heights of the bars are all clustered around the numbers 40 through about almost 70, not quite. And on the right, we see the bars. You can see that they're flatter. They're not as high as the ones on the left. The bars are flatter and they tend to vary from 20 to 90. So here things go from 40 to 70 and we have this high frequency. And in the graph on the right, things go from 20 to 90 with a not as high frequency. Okay, notice the heights of the bars are less. We're going to say when we see a difference like this, we have a higher standard deviation on the right. Now, higher standard deviation means that we have greater variability. So we have more, things are more spread out more when we have higher variability on the right here, ability. We have more of a clustered effect, and we have low variability when we see a graph like the one on the left. Okay, these values are more clustered, whereas these values are more spread out. So higher dispersion, more spread out means higher variability up here. More clustering means lower variability, which is what we have here. And since the standard deviation is a measure of variability, this one has the high standard deviation because it's more spread out, and this one has the lower standard deviation. because it is clustered. Okay. Let's look at a clinical trial example. A clinical trial is conducted to test the effectiveness of two different fictional drugs. Okay, these are made up, CardioEase and LipoClear, in lowering cholesterol levels. After 8 weeks, the reduction in cholesterol for each patient is recorded. So we have two data sets, one for patients on CardioEase, one for patients on LipoClear, and these are the reduction in cholesterol levels. So a reduction of 20 points, 22, 24, 26, 28, a reduction in 10 points, 15 points, 20 points, 30 points, 40 points. Calculate the mean and standard deviation for each group. We have to use the correct symbols for each. What do the calculations tell you about the two drugs? So to calculate the mean and standard deviation, we are going to put each list into, or each set into a list on our calculators. We're going to calculate one var stats for each of these. We're going to take note of the mean and standard deviation using the correct symbols. So remember that if we're dealing with a clinical trial, this is only done on a sample of patients, so the correct symbols would be X bar for the mean and S for the sample standard deviation. And we'll do that for CardioEase, and we're going to do that for LipoClear. And then we're going to determine what they tell us. What does the mean tell us? What does the standard deviation tell us? So let's go to the calculator and put these two data sets into two different lists. Okay, let's press Stat, Edit. I'll erase what's in L1. And I'll put in these cholesterol decreases for CardioEase. And then L2, I'll put these cholesterol decreases for LipoClear. Okay, I'm going to run stat calc one of our stats on L1 for CardioEase. And I have an average of 24 and a mean of, a mean, which is the average of 24. I'm going to write this on the slideshow that I'll share with you after. And a sample standard deviation of 3.1623. So I'm looking at this row, 3.162, but then this 7 tells us we're going to go up this to a 3. Let's go to stat, run stat, one var stats again, this time on L2 with LipoClear. Okay, this time our sample mean is 23. So it was 24 with CardioEase and it's 23 with LipoClear. That's not too big of a difference, and not too big of an average difference, but the sample standard deviation here is 12.0416. Okay, that gives us a lot of information. Let me go back to the slideshow. Okay, so I took note of those numbers while the calculator was on. 24, the mean for CardioEase, and 3.1623, the standard deviation. 23, the mean for LipoClear, and 12.0416, the standard deviation for LipoClear. So this mean is not too drastically different between the two data sets, but the standard deviation definitely is much different between the two data sets. It's much bigger for LipoClear. And from the previous slide, what we were talking about big standard deviation versus small standard deviation, the bigger standard deviation is an indicator of big variability. So big variation from one patient to the next, which if we examine these numbers, that's kind of what we see here. Whereas smaller standard deviation means small variability. So not too much difference from one patient to the next. So this is how we would verbalize this. We have these two sets of numbers that we have gotten from the calculator. The interpretation. Let's interpret the mean. The average reduction for cholesterol is 24 mg/dL for patients taking cardio-E's. The average reduction in cholesterol is 23 mg/dL for patients taking Lipoclear. Okay, so that's how we interpret the differences in the sample means, which isn't too much of a difference at all. But now let's interpret the standard deviation. The standard deviation for patients on cardio-E's is 3.1623 mg/dL, and the standard deviation for patients on Lipoclear is 12.0416 mg/dL. So we can make this interpretation here. Cardio-E's has more consistent cholesterol reductions across patients as shown by the smaller standard deviation, which means low variability. So more consistency is what we see when we have lower standard deviation. Lipoclear has much larger spread in the results. Patient responses varied more widely from modest reductions to much larger reductions. And this is what we see with high variability. So that's the comparison between two standard deviations and what it means in this cholesterol example. More applications of the standard deviation. It is a very, very commonly used measure in many data sets. Monitoring vital signs, for example. In critical care, the standard deviation of heart rate can help assess a patient's stability. A small standard deviation might indicate stable condition. So small standard deviation in heart rate, stable heart rate, consistent numbers, low variability. Large standard deviation could suggest arrhythmia or other irregularities that need close monitoring. Okay, large standard deviation in heart rate could be very urgent. Assessing treatment effectiveness. When treating diabetic patients, tracking the standard deviation of blood sugar readings over time helps doctors understand how well blood sugar is controlled. So if I'm looking at a standard deviation of blood sugar and my standard deviation is low, it means that I have consistent blood sugar measurements. They're generally not too variable, they're consistent and similar, and there's not a lot of ups and downs. Whereas if I had a high standard deviation in my glucose measurements, it would suggest that blood sugar is fluctuating significantly. So lots of ups and downs, big jumps from blood sugar measurements to the next, possibly requiring adjustments to insulin or medication, or perhaps diet. So for real-world applications in healthcare, the standard deviation is often the most useful measure. It is easy to interpret. It can reveal whether data values such as vital signs or treatment outcomes are consistent or spread out across a population. So consistency is ideal for most applications. When things are variable or spread out, oftentimes we like to rein them in and have them be closer to the rest of the values. So one more example, similar to the cholesterol example, let's look at a clinical trial to test the effectiveness of two physical therapy programs in improving shoulder range of motion after an injury. So we have two groups. Flexicare is following a low intensity stretching program for gradual improvements. And then there's another group following the Motion Max program with high intensity rehab aimed at quicker results. So we have Motion Max and their range of motion improvements. This is in degrees. And Flexicare, their range of motion improvements. Okay, so I should have reversed these. Flexicare was the one that was low intensity, and Motion Max, the second one, is high intensity. So like the example with cholesterol, let's put these into two lists and analyze what the mean and standard deviation tell us. So let me just put this here. I'm going to put X bar and S for the mean and standard deviation on the slideshow as I find them from the calculator. Okay, so let's go and put in, I'm going to overwrite L1 and L2 with these 5 new values for Motion Max and Flexicare. So Motion Max 10, 12, 18, 25, 30, and Flexicare 15, 17, 18, 20, 22. Running one var stats on Motion Max, that's in L1, so second one, gives me an average sample mean of 19 and a standard deviation of 8.4853. And let's do the same thing with Flexicare in L2. X bar is this time 18.4 and the sample standard deviation is 2.7019. Okay, so I pulled out the mean and standard deviation for both data sets. Like before, it doesn't appear that the means are very different between these two different physical therapy programs. The average improvement in degrees of motion are generally the same. 19 and 18.4 are the averages, not too different from one another, but the standard deviations are different. So Motion Max has a larger standard deviation than Flexicare. And what does that tell us? So putting these all together, the average improvement in shoulder range of motion is 19 degrees for patients in the Motion Max program. The average improvement in shoulder range of motion is 18.4 degrees for patients in the Flexicare program. And the standard deviation is for Motion Max is 8.4853. Standard deviation for Flexicare 2.7019. Okay. So the spread is measured by the standard deviation, and what we see is a larger spread in Motion Max because its standard deviation is bigger than Flexicare. What that means is patients' responses are varied more widely from modest improvements to much larger improvements. There's high variability in that group. So the numbers go from very low to very high. Whereas in the Flexicare group, we have more consistency in those results. Those improvements are more consistent. There's a smaller standard deviation. We have low variability. So the values are more clustered closer to one another rather than spread out far away. So that is the gist of standard deviation and measuring variability in data sets. We are going to be using this measure, the measure of variability called the standard deviation, very, very much throughout the rest of this course. So if you need to come back to this lecture at any point to view how we calculated these numbers, please do. And this definitely gives you enough to do your homework, though, the homework assignment for homework 4. And thanks for sticking with me, and I'll see you at the next lecture.